Okay, next we're going to talk about subspaces of Rn. So what is a subspace? Well, you have to start with the notion of a subset. So let's start by assuming, first and foremost, before we go any further, let's assume that we've got a subset of Rn, and we'll call it H. So what does that mean to be a subset of Rn? It just means that H is a collection of vectors. It might have just a few vectors. It might have many vectors. It might have infinitely many, in fact. There's a lot of different possibilities at this stage. But the idea is you've got a collection of vectors and they all happen to be in Rn, which means they have n coordinates, whatever n might be. Okay, so you can, if you have that, now you can go further and say that that subset H is actually a subspace of Rn. And I'm going to underline all of this in red, not just the word subspace, but all the way to of Rn, because this is all one phrase here. So, okay, well, what does it mean to be a subspace of Rn? It means that the next three conditions in this list, well, the three conditions in this list, I should say, are all satisfied. So the first condition, let's look at this one. The first condition says that the zero vector belongs to H. Remember, H is a set of vectors, right? It's some collection of vectors. So every vector in Rn has the property that it's either in H or it's not. It's one or the other. But in the case of the zero vector, it had better be in H. Otherwise, this first condition wouldn't be satisfied. And if H wants to be a subspace of Rn, it's got to satisfy all three of these conditions. So if the zero vector does belong to H, well, then you can keep moving forward and look at the next condition in the list. So what does this next condition say? It says, if you read it one symbol at a time, you'll see x plus y is in H. Okay, well, what's x and y, right? And you have to finish reading the sentence before those symbols are quantified. But in the second half of the sentence, it says whenever x and y are in H. So now that you've gotten to the end of the sentence, you can put everything together and see what this condition is actually saying. It's saying that if you start with two elements of H, any two vectors that happen to belong to H, if you add them together, you're going to get another vector, right? Because if you take two vectors and add them, you're going to get another vector. Well, that vector that you get as a result of adding the two vectors x and y together, that had better also be in H. Okay, so that's a bit of a long way to word it. So let's see if we can clean that language up a little bit. First of all, this is sometimes referred to as being closed under addition. But roughly speaking, here's probably the simplest way to say it. If you take two vectors in H and you add them together, the result has to also be in H. Okay, so if you can find two particular vectors that are known to be in H and you add them together and then the result is not in H, well, then that's exactly what it would mean for condition 2 to fail. It means it's possible to do that. Okay, what about condition 3? The structure of condition 3 is similar to condition 2, but it's a slightly different property. So the first part of the sentence says that k times x must belong to H. And again, if you just stop reading at that point, you're going to say, well, what is k and what is x? But you have to keep reading to have those quantified. So whenever x is a vector in H and k is a real number. So what you're really saying here is that if you start with a vector in H and you multiply it by any scalar, the result has to also be in H. That's what this third condition is really requiring here. Okay, so, and just like with the second condition, there's a nickname for this. This is referred to sometimes as the closure of scalar multiplication, or to say that H is closed under scalar multiplication. Okay, so what do these things look like? Well, roughly speaking, they're straight objects in space. So you've actually already encountered a few examples of subspaces, or at least two. The natural examples being lines and planes, right? They're straight objects that go on forever. That's really what this definition is encapsulating. But this is an algebraic definition of the concept, and those are actually more powerful because they work in general. If you don't have to describe something geometrically, then your explanation or definition will work in higher dimensions as well, and that's what makes them powerful. So, well, how do you get your hands on these spaces? Well, remember how the first time we introduced a line, it was the span of a non-zero vector. And the first time we looked at a plane formally, it was the span of two vectors that had the additional property that they, first of all, they were both non-zero and that neither of them were multiples of the other. Well, we've actually got some new language that allows us to say that more concisely. We can say that the two vectors are linearly independent. If you take the span of two linearly independent vectors, you're going to get a plane. Now, in R3, I should say, I should add a qualifying statement. That's if you're dealing with R3. But what about in general? If you take the span of any number of vectors in any dimensional space, let's go up to Rn. What if I took the span of several vectors in Rn? What's going to happen? And it turns out, I don't want to spoil the surprise and get too far ahead of myself, but it turns out that you're going to get a subspace in that case as well. But what I want to do is just restrict ourselves to the simple case where we're taking the span of two vectors, and I want to prove to you that that's always going to give you a subspace of Rn. And then the idea is the argument that we use, it keeps it as simple as possible because there's only two vectors in this span. But the idea is that the argument we use here will generalize very naturally to cases where you have more vectors in your span. Okay, so let's prove this. What is the statement? We've got two vectors, v1 and v2 in Rn, and we want to show that H, which is the span of those two vectors, is a subspace of Rn. So we just need to satisfy that under these conditions, H satisfies each of the statements 1, 2, and 3. Okay, so let's start with the first statement. Is the zero vector in H? Well, what's H? It's the span of v1 and v2. Well, wait a minute. What is span? Right? It's easy to forget with all these terms, right? So you have to, and if you don't remember what span is, again, this is another case where if review is important, right? And if you let these terms kind of fade away into the background, then it becomes harder and harder to follow the course. But I'll just remind you, the span of a collection of vectors, in our case we have v1 and v2, this is the set of all linear combinations of the vectors v1 and v2. Okay, so, well, what does that say about whether or not the zero vector is in H? Well, can you write the zero vector as a linear combination of v1 and v2? And this is a question we've actually asked before. The answer is yes, you always can. You can always write the zero vector as a linear combination of anything. Just remember, when you're writing a linear combination, you choose a weight for each of the vectors, right? Each of those vectors has a weight, which is just a scalar assigned to it and multiplied through scalar multiplication. Well, if I choose all those weights to be zero, so in this case, I'll just say 0 times v1 plus 0 times v2, then this will always give me the zero vector because 0 times v1 is the zero vector, 0 times v2 is the zero vector, and if I add the zero vector to itself, I'm going to get the zero vector again. So for that reason, well, those reasons I should say, you can always express the zero vector as a linear combination of any other vectors at all. So this is now explicitly written so that it is a linear combination of v1 and v2. So it's safe for us now to say this belongs to H, and we can expect that there will be no argument against that. Okay, so that was quick, right? But that's how you verify the first statement. And quite often, the first statement is the easiest to check, whether it's true or whether it's false. It's going to be the least amount of work to actually investigate. It's the other two statements that can sometimes be tricky. Let's take a look at the second condition. So we've got, okay, we need to show that if any two vectors are in H, their sum is also in H. So let's start with the assumption that we've already got two vectors in H. So let's say I could write the word assume here or suppose, it would be the same thing. So let's say let X and Y be in H. And really what I'm doing when I write something like that, what I'm saying is that all the work that I write down afterwards is going to be under the assumption that this is true, okay? And that fits in very nicely with what we're trying to show here, because we're just trying to show that this is true, but only when this is true, right? We don't need to show that X plus Y is always in H for any values of X and Y, because if that were the case, well, then the only thing that would be a subspace is Rn itself, and that wouldn't be very interesting. We want to allow for smaller sets to also be subspaces. So we only need to show that X plus Y is in H under the assumption that X and Y are also in H. So that's why we're going to start with the assumption that X and Y are already in H, and then we're going to show that their sum is also in H. Well, what does it mean to be in H, right? H wasn't just some symbol, right? We know what it means. H is the span of V1 and V2. It's the set of all linear combinations of V1 and V2. So that tells you something about X and Y, right? So that we can do this. We can say that X is a linear combination of V1 and V2. So I'll just use C1 V1 plus C2 V2, right? That's got to be true for some scalars C1 and C2. And I can also do the same for Y. I'll write Y. But now I'm not going to write C1 V1 plus C2 V2 because I've already used those symbols for the weights when I represented X as a linear combination of V1 and V2. But if I'm going to do this with Y now, I'm nowhere in our work do we want to depend on the assumption that X and Y are the same vector. That wouldn't be very good at all. So we want to allow for the possibility that they might be different. So we should use different symbols for the coefficients. So I'll say D1 V1 plus D2 V2. And then let's finish this off. To be grammatically correct, we should say for some C1, C2, D1, D2 in the reals. So we're just making it absolutely clear that, hey, C1 and C2, we don't know what they are, but if just from the assumption that X and Y are in H, there's got to be some scalar C1, C2, D1, and D2 that makes these two equations true. And that's all we're going to need. We don't need to know what they are. We just need to know that there is some appropriate values that make these equations work. Okay, so that's about all you can do from the assumption. That's about all you can say about X and Y. If we try to be any more specific, then our argument won't hold in general. And we want to make only the assumption that X and Y belong to H. Okay, so what are we trying to show? We're trying to show that the sum of X and Y is now also in H. Okay, well, let's start by figuring out what the sum is. So let's say X plus Y. Okay, so we're going to add them together and see what we get. Well, we've actually got representations of X and Y in the form of linear combinations. So we've got C1 V1 plus C2 V2. That's our vector X written as a linear combination. And then we've got Y is D1 V1 plus D2 V2. Okay, so we want to add those together now. Well, what we're going to do is we're going to collect like terms. Remember, addition, this is vector addition. So the brackets, they're not really doing anything, and the order is not super important, right? You can add vectors up in either order. So we can freely interchange the order of these terms, and ultimately we'll be collecting like terms. And what you're going to get here, once you do that, is I can write this as C1 plus D1 times the vector V1. That's a scalar product. What I got that from is essentially just taking this term, C1 V1 and D1 V1, and adding them together, and that gave me this here. And then what I'm going to get when I add up the other two terms is I'll have C2 plus D2 V2. So what I'm doing here is I'm adding up this term and this term directly, and I'm just factoring out the V2. And that's going to give me this term here. And here's the essence of this argument. What are C1 and D1? Let's start here. What are C1 and D1? C1 and D1 are just real numbers, right? C1 and D1 are just real numbers, and we're adding them together. So we don't know what we're going to get, but we do know that we're going to get another real number. That much we can say for sure. And same with C2 and D2. You don't know what C2 is, and you don't know what D2 is, but you do know that when you add them up together, you're going to get a real number. So what you have here is something of the form a real number times V1 plus a real number times V2. But that's exactly what a linear combination would look like, right? That's a linear combination of V1 and V2. So what was H? It's the set of all linear combinations of V1 and V2. So that means we've found one of those linear combinations, so it's got to be in H. And that is how we finish off the argument for verifying that statement 2 is correct. So I'm going to draw a bracket here. You don't have to do this, by the way. These brackets, this is just something I've just introduced. I'm hoping that it helps make sense of things later. When you're looking back on these notes, you can see, okay, all of this work is the verification of statement 2. It just allows your eyes to know what to read. But anyways, okay, so that's the verification of statement number 2. Now we need to verify statement number 3 is true. And we're going to approach this in a similar way. What do we have to do? We have to show that k times x is in H. But that only has to be true under the assumptions that x is in H and k is some real number. So let's start by making that assumption. Let's say, let x be in H and k be a real number. Okay? So that is the assumptions that we make in this case. So we've already assumed that this is true now. So it's up to us to prove that k times x is also in H. Okay? And we're going to start out in the same way. Right? This gives you something. The fact that x belongs to H is not just some unknown set. It's a set whose definition we were given in the problem. It's the span of V1 and V2. So that means x is a linear combination of V1 and V2, just like it was up here. So the first little bit here is just going to mirror what we did the first time. So we can say x is equal to C1 V1 plus C2 V2. And that's for some scalars C1 and C2. So for some C1 and C2 in the real numbers. Okay, so now we're going to we're going to multiply the vector x by the scalar k. So, okay, and then cross our fingers and hope that once we're done that, we'll be able to show that the result belongs to H. Okay, well, how is that going to go? Well, there's only one thing you could do at this point, right? We've got k and we're multiplying it by x. Let's replace x with our linear combination over here. So we've got C1 V1 plus C2 V2. Okay, and then, well, what's going to happen there? Well, we've got two terms that we're multiplying by the scalar k. One of the properties of scalar multiplication is that it distributes into vector addition. So this is going to give us k times C1 V1. I've put the brackets so that they group the scalars together, plus k times C2 V2. Okay, and then now I can do a similar sort of observation. I don't know what k is, and I don't know what C1 is, but I do know they're both real numbers. So I can say their product is going to be a real number. And same with the k C2. I don't know what k is, I don't know what C2 is, but I do know they're both real numbers. So their product is also going to be a real number. So that means I've got a real number times V1 plus a real number times V2. That's exactly what it means to be a linear combination of V1 and V2. So therefore I can say this belongs to H. Okay, and that completes the proof because that's what we needed to show. We needed to show that if k is a real number and x is a member of H, that k times x is also a member of H. That's what we started with, right? K times x, it was equal to this, which is equal to this, which is an element of H. So this line really does say what we wanted. Just like over here, this line really did say that x plus y is in H because x plus y is equal to all of this, which is equal to all of this. All we did is just rewrite it into different form twice, right? But in the end, we got something that clearly belongs to H. So we can say that we've proved that statement there. So now we get to tie these things together and we can say therefore H, which was the span of V1 and V2, is a subspace of Rn. Okay, so I mentioned that this argument generalizes, and this fact is going to do the work there and make that clear. So how does this generalize? So here's the fact. If you start with any list of vectors in Rn, notice it's not just two vectors, V1 and V2 anymore. It's an arbitrarily long, finite list. There could be many. P could be like 50 or 1,000, right? P could be huge. But if you have a list of vectors in Rn and you take their span, so that means, in other words, you're taking all the possible linear combinations you could form with those vectors. And if you have a lot of vectors, then there's going to be a lot of linear combinations that you can form. But when you put those together into a set, you're going to get a subspace of Rn. That's what this fact is saying. And this actually is a special subspace, and it has a name. It's the subspace of Rn, which is generated by those vectors V1 through Vp, or we also say is spanned by those vectors. You may have heard me use this language already and sneak it in a time or two, but that's the language we use. Okay, so back in this case, H is the subspace generated by V1 and V2. H is the subspace of Rn that is spanned by V1 and V2. Those would both be perfectly reasonable ways to say it out loud. And why is this fact true? Well, essentially for the argument that we gave, although if you're being picky, you'd say, well, our argument only shows that this is true when you have two vectors. Well, the argument's the same, right? If you have more, if I had, say, the span of V1, V2, and V3, the proof would change a little bit, right? Here's where it would change. As soon as we assume that X was in H and Y was in H, then we'd have, when we go to write X and Y, we'd have to have three terms instead of two. So you'd have something like X is C1V1 plus C2V2 plus C3V3, right? And then Y would be D1V1 plus D2V2 plus D3V3, and so on. So you'd have a few extra terms there. And of course, you'd have to make some modifications to this line. But then what would this look like? I claim that this line would be almost the same, right? You'd have C1V1 plus C2V2 plus C3V3. Here you'd have D1V1 plus D2V2 plus D3V3. And then when you go to collect all your like terms, these two terms wouldn't change, but you'd have an extra one added on afterwards. You'd have bracket C3 plus D3 multiplied by V3. But in fact, that's exactly what you would need to have a linear combination of V1, V2, and V3 to actually draw the conclusion that your sum is in H. So the argument is almost the same. It just gets a little bit more complicated the more vectors you have, but the underlying idea is the same and the structure is the same. So anyways, let's end this video on just a reminder of this fact. If you take some vectors, any vectors, V1 through VP, let's say you index them like that, take their span, the result is going to be a subspace of Rn every time, guaranteed.